Good afternoon, dear colleagues. My name is Anton Sonuyshkin. I'm the head of the Department of Remote Sensing Data Processing Center and also one of the developers of the SCANEX product image processor, which had been introduced to you by my colleague Ilya Farutin already. In my presentation, I would like to mostly focus on the algorithm owing to which we could considerably increase the speed of auto-rectification of data in our program. Our program SCANEX image processor is its main distinguishing feature is that the image can be auto-rectified or just transformed in the mode similar to real time. All the information can be seen on the screen of your computer, and you can visually control the quality, and also the speed of processing is greatly improved. And we can also note here that there is no need to do resampling during thematic interpretation, which can maintain the source characteristics of radiometric images, which helps a lot during thematic interpretation, which can help us avoid various brightness distortions. What is this and how does it work? In principle, the idea was very easy. During the uploading of any image to our system, we built a regular net grid of latitudes and longitudes with the regular pixel steps. You can see it on the slide. The coordinates of pixels lying between the nodes of this grid can be easily calculated by linear interpolation, and all this image can be superimposed on the screen of the computer in the required system of coordinates or projection. If the customer, or not the customer, maybe the user of our software needs to save it in the form of a file, then you can easily resample and rediscredit the brightness by using one of the available archive filters. A couple of words about where these grids come from. First of all, I need to note that such grids are often supplied by suppliers of source data, like for instance MODIS program data, RadioSat 1 and VSAT. Virtually, well, there are many software programs which can generate such grids, but on the other hand, they do not take into consideration the deviations or in the relief or elevation, and all of them are based on the flat elevation, and but we do take into consideration for that. We can use either a strict approach, it is quite easy and self-evident, or the reverse RPC model, where we calculate the linkage between the pixels and longitudes and latitudes and the system of coordinates of the object. As a rule, especially as far as it applies to the super high resolution, the inverse RPC models eventually are not provided to the end users, with the exception of Pleiad maybe, and Spot 6 and 7, and mostly we use direct RPC model with the linkage between longitude and latitude predetermines the linkage with coordinates in the image. In this case, you can put down this formula mathematically. If in the input we have coefficient of rational multi-member and the function which returns altitudes by latitude and longitude of the object, we can, and the initial approximation of coordinates with the grid, we need to find the corrections to the nodes of this grid. Well, let us not to think too hard about it. Eventually, it boils down to simple linear equations. But unfortunately, we sometimes come up with a situation, especially when there is a big deviation of the equipment from nadir. and the rational function can return from one point on the image. I'm sorry, no, not what I wanted to say. For longitude, latitudes, and altitudes, it can return same pixel coordinates on the image, or during different latitudes, longitudes, and altitudes, same number of the pixel can return. It can happen when the image ends up in the dead zone, or other way around from the different side. This slide actually shows the result of performing such an operation, and our grid can be considerably distorted. It can have many crisscrossings, and in order to avoid these crisscrossings, we do additional verification, where we can find and filter them by using splines, and then we can rectify it like this. On the top slide you can see the grid, and at the bottom you can see the grid smoothed out after subsequent processing, and a few examples of how and what it looks like on the live image. To your left you can see the source image transformed to the medium altitude of the surface, then orthophoto generated by traditional method, and to your right the orthophoto generated by grid method. In this case you can clearly see on the middle image we see doubling of brightness of pixels that end up in the dead zone, which led to the false tear line, and by using grid method we physically cannot get the same result as on the central image, because our pixels on the screen are not changing. The size of raster remains the same. That's why we have such elongations. And about similar situation we have with the second problem on the central image. Again, you see traditionally generated orthophoto. On the right you can see grid method, and the source image to the left. Again, you see different deviations of extreme edges on the cliff. Everything looks beautiful on the picture, but to say that people can use this, for that we did quite a thorough testing of this model with different characteristics. As testing ground we used Maison-les-Halles in France. This is an interesting place because they have quite a pronounced elevation there, and almost half of this area is mountainous. That's why more than 4% of this area has extreme angles and slopes. We installed 33 points for altitude preparation by using special precise equipment, and we use different digital elevation models with different density and precision. As data sets for testing, we used images from QuickBird with large range of angle deviation in nadir. Basically, we had both an ideal case and very extreme cases as well. And the next shows the digital elevation models. And initially, we had a dense digital elevation model built based on an ADS-40 using special rectification and processing, and also digital elevation model for topographic map of scale 1 to 25,000, and digital elevation model available in open sources. That would be DEM generated by interferometry based on X band from SRM-XR, SR-GDM, DEM, and SRTM-SIRC DEM. As long as density varied quite drastically, we decided to generate a fuller picture, to add 2 more digital elevation models, and they were built by ourselves by using 2 images which were taken close to each other. One had the deviation angle of 2 degrees, another 16 degrees. Of course, it's not an ideal stereo configuration, but the dates were very close, and we could get something similar to real elevation. And also panchromatically speaking, through global collation, we built DEM with density of 0.6 meters, and also we built 2 DMs with 5 and 10 meter steps, but through the method of global optimization that our software is capable of. Using global using ground control points, we could or checkpoints, we could check the accuracy. You can see it at the bottom, and eventually we wanted to provide an objective view of approximation of our model, RPC model. We studied the accuracy level for each pixel for all orthophoto plans. For that we built 5, for each image we built 5 grids with 2, 4, 8, 16 and 32 pixel steps, gaps, and also taking into consideration all the digital elevation models available to us. Also, we built using traditional methods orthophotos based on the same DEMs, but in order to compare these coordinates pixel by pixel. During orthorectification, we preserved 2 matrices in the basis of orthophotos, which recorded the pixel coordinates on X and other for Y axis of the image, which helped us to get the full set of data so that we can pixel by pixel follow the deviations of one method from another. Eventually we calculated the difference in coordinates. We calculated a huge number of various characteristics, including the percentage of the error and what percentage of error ended up in each one of these models. And this slide, indeed we had to operate with a lot of data, and here I will show you only the root mean square, and it shows that if the density of the digital elevation model is not over 10 meters, then in all cases, independent of what was the step of the grid of ortho transformation, we get sub-pixel accuracy. And the increase in the density of the EM, we start seeing the trend towards increase of root mean square error. And in the first suggestion, we made a conclusion that it is related to our dead zones, where with a big expansion or stretching or big density. To make sure that it is really so, we did an additional study. We took the most extreme case with the image with the degree of 35.3 degrees of deviation from nadir, and we used the most precise DEM that we had, the most dense one that we had. We built the map of dead zones and the map of surface angles, and analyzed what would be the likelihood and in what intervals these errors end up in different, how these errors are spatially distributed over the image. And this slide shows that all the errors, about more than 0.5 meters, happen with the angles over 20 degrees, and all the maximum errors usually are concentrated in the areas of dead zones in dead zones, in other words. At the same time, I must note that smaller gaps in the grid, unfortunately, in extreme case, doesn't ensure subpixel accuracy based on the RMS error value. This slide shows the optimal, in terms of subpixel accuracy, the optimal pace between the grids and in the grid, and as a ballpark figure I can tell you that the average gap in the spacing in the grid must be proportional to the spacing in our digital elevation model to get a subpixel accuracy. And eventually the productivity of this method is shown here. All 5 grids are here, and the result of this operation can be seen that in some cases we can improve performance by a matter of by 25 or 27-fold. And eventually I would like to invite everybody to our tomorrow's workshop, where we're going to give you a live show how these things work, and you'll see how to build dense DEMs and how this orthorectification works. One thing is to see it on the slides, another to try it yourself. And also all the people who will come tomorrow, my colleague Ilya promised to give you an evaluation trial version. This is a temporary or provisional license, which if you like, you can buy the full version later on. Thank you very much. I enjoyed this presentation immensely. Thank you. Are there any questions for the speaker? No.